Welcome to qnawire.
Hi there. So for this problem, we need to determine how far from the foot of the cliff does a ball land and how fast it is moving just before it lands. So we are going to determine this distance that we call d and the speed of the ball just before it lands. So we need the final velocity and also the distance d. And the way that we are going to do this is by using first conservation of energy. At this point, just before the ball, the ball falls from the cliff, and with that information, we can obtain the final velocity in that point, and that will be our initial velocity to consider when we are going to find the velocity at this position. And to do that, we are going to use the equation for the equation of kinematics that relates the height with the acceleration. And in this case, because it is following the acceleration due to gravity, and this will give us a time. And using that time, we can determine the horizontal reach that is called d in this case. So I'm gonna do just that. So beginning with conservation of energy, we have that. We know that when something, we are going to set this first in here, that this is the zero of potential energy. So we begin with zero potential energy because it's at the zero. And so we will have only kinetic energy. We know the form of kinetic energy. This is 1/2 of the mass of the ball. And this is the velocity, the initial velocity squared, plus we know that the ball is rolling up this cliff. So this hill, sorry. So we will have also rotational kinetic energies, and that is the for 1/2 of the momentum of inertia times the angular velocity squared. And this is initial, of course, and the final thing, this of course is the initial velocity equals to the final velocity. That is the conservation of energy. So for the final part, we have the translational kinetic energy plus the rotational one. And we also know that at this point on top of the hill, we will have also potential energy, and that is plus GHM, and H in this case is 28 meters. So once set this equation, we first need to know all the variables that we are not given for this problem. And for instance, we don't know what is the momentum of inertia. We also don't know the angular velocity, and that's it. So we can find this value in a table, and for an spherical solid sphere, the momentum of inertia is 2/5 the mass of this ball times the radius, its radius square. So that is the momentum of the inertia. We also know that the ball is rolling without slipping. So that is a condition in physics. And it means that the angular velocity can be expressed as the translational velocity p over r, over the radius of the sphere in this case. So knowing this, we just need to substitute all of this in the equation for the conservation of energy. So we will have 1/2 of m be the initial velocity squared plus, here we substitute the values that we know. The angular velocity, the initial angular velocity is equal to the initial translational velocity over r, and the final one is with the final translational velocity. And for the other side, we will have then this is the final expression for the conservation of energy. We could see that we can eliminate some terms in here that are repeating in both sides of this equation. For instance, the mass, all of these masses we can eliminate. Also in here, because it is to the square, we eliminate the radius in here, and that's it. That's all we can simplify. So writing down that equation simplified, we obtain this equation, and we can simplify further by looking that these two are the same and these two are the same, so we need to sum 1/2 plus 1/5, and the same for the other part. So summing this, we obtain this equation. So finally, we need to solve for b, and that will give us the square root of this pass to the left side by a negative sign, and we just need to all of that. So this is what we have by solving for BF. So this is expression for the final velocity just before the ball falls from the cliff. So we need to put all of this information. We know that we know the initial velocity, which is the initial velocity is 25 meters per second. We know h is 28, and we know that the acceleration due to gravity is 9.8 meters per second. So we plot all of those values in here. Something like this. And plotting all this into the calculator, we obtain 15.26 meters per second. Now with this value, we can determine how far from the cliff the ball lands. But first, we need to determine how long it takes for the ball to land, so that we can take the value of d by just multiplying this final velocity to that time, and then obtain the horizontal reach. So to find that time, we can use the fact that we are falling from a cliff that has a height h, and we know that height. So we can use this formula of kinematics. Um, and we know that the initial velocity in the y component is 0. We know that the final height is 0, just because it lands in the ground, it is 0. And we know that this in here corresponds to the height of the cliff. So we just solve for that and we obtain that h is equal to 2 times g t squared. So we just simply solve for t, and we obtain that this is equal to the square root of h over 2 times the acceleration due to gravity. So substituting that values, we know that this is, we obtain a time of 2.39 seconds. Now, we just simply, to obtain the distance t, that is the horizontal reach, or yes, the horizontal reach, we know that that is just the velocity times that time that the ball takes to get to the land, so to the ground. So we know this velocity because we just determine it from conservation of energy, so that it will be 15.26 meter squared times that time, which is 2.38 seconds. And this gives us a value of 36.5 meters. And this is our fair result for this exercise, that the distance d from the cliff is 36.5. Now we want to determine the velocity of the ball just before it lands. So we know that the horizontal velocity, or the x component of the velocity that we determine in the conservation of energy, doesn't change because we don't have an acceleration in that component, but we do have an acceleration in the y component, and that is because we are being accelerated with the acceleration due to gravity. So to find that final velocity, it asks for the how fast it's moving. So this is the speed, so it should be like the square root of the x component and the y component. We already know that x component from conservation of energy, but the one from um, the y component, we can determine it by kinematics, by knowing that this equation, the final velocity is equal to the initial velocity. In this case, we're going to put it in the y component just to differentiate. And in this case, this is minus 2 times the acceleration due to gravity. No, sorry. And this is plus the acceleration times t. So we know that the initial velocity is 0, And the acceleration corresponds to the acceleration due to gravity, so that the final velocity in the y component is just um, this, which is 90.8 meters per second squared times the time it takes to get to the ground, which is 2.38 seconds. So calculating this, we obtain a value of 23.32 meters per second. So plotting these two values in the equation for the speed, we will have that the velocity in the x component is this one. So it's this plus the one that we just determined. And this gives us a value of 27.87 meters per second. So this is the velocity at which the ball is just before it lands. And the final question for this problem is that we notice that the ball lands, it has a greater translational speed. And that means that when it is at the bottom of the hill, so at the initial position, and we need to determine what this is mean. The ball somehow gain energy? And the answer is no. The ball does not gain energy when it leaves the cliff. The solution for this is that instead, less kinetic energy is used for the rotational kinetic energy, and then it is able to be used for the translational kinetic energy. And the total energy of the system is conserved. And we just simply know that when it is falling from the cliff, it just doesn't it is not rotating, so that energy goes to the translational energy. But if you compare the initial translational kinetic energy and rotational kinetic energy from the bottom of the hill and compare it to this final kinetic energy, we will have that the energy is conserved. So no, the answer is no, and the ball does not gain energy